tonight we have Nicole Myers here giving us a presentation about the coastal geology of the northern coast where we're all, well, I don't know if all of you live here, but I do and feel real lucky about it and very curious. She has an MS in geological sciences. She developed a passion for understanding the earth from a childhood fascination with rocks and volcanoes, and now teaches others to appreciate planet Earth. Nicole told me that she has taught every earth science that there is. So this includes geology, climatology, and earth history for more than 18 years. She currently teaches at Sonoma State University and also through her organization Appreciating Earth. She brings her enthusiasm to the community by authoring earth science field explorations and presentations. So you can go on geology walk and presentations and things like this with Nicole as well, which I think would be really cool. So that's a little bit about Nicole. As I mentioned, there's no fee for our science talks, but we do appreciate your donations, which help to support our programming. So thanks everybody for being here, and especially thanks to Nicole for coming and taking some time out of your evening to share your knowledge with us.
Thank you so much for having me. I love talking about everything related to the earth. Um, I have done this presentation, or at least a version of it before, because so many people are in love with the ocean. The ocean is spectacular. But part of what I hope to share with you is why the coast off of California, why the ocean is shaped the way that it is. As in, when you leave the coastline, how deep does the water get and how fast, and how does that depth change? And then even to take a trip back into deep time and better understand how our coastline has changed over time and what series of events have actually led to the shape of the coast that we get to love today. So, part of what I'm going to talk about is the development of the California geomorphic provinces, fancy words, specifically focusing on the coastal ranges and recognizing how the coastal ranges that make up so much of the coast of California are the result of tectonics, plate tectonic movements. We're also going to look at bathymetry, the shape of the ocean floor. Bathymetry is just a word that's similar to topography, but for below sea level. And then I also want to talk a little bit about how water flow has changed over the course of time. And so in this map on the left, you can see there's this channel that flows beneath the San Francisco Bay, and to better understand when that channel developed and when was it a river, because it has not always been a below sea level channel. I will be focusing on the geologic history of Northern California, but I'm going to have to talk about Southern California a little bit here and there too, because the coast of California has shifted so much that many of the rocks that we find along our coastline actually originated in Southern California. So I'll be focusing on tectonic history, volcanic past, and coastline evolution. I am starting with the assumption that all, if not most of you, do not have a lot of geology background. So that is my starting assumption. I wanted to introduce both the geologic timescale, which is the geology calendar, and the materials that are most important in geology, aka the rocks. So here on the right, I have the geologic timescale. The calendar that you and I use on a daily basis is called the Gregorian calendar. And we measure days and weeks and months and years via the Gregorian calendar, but it is thoroughly useless once we start talking about thousands and millions of years. So you can think of this geologic timescale as essentially the calendar for deep Earth time. Now, I chose one that's beautifully color coded, but it's not entirely complete. Earth time goes back to 4.54 billion years. So I'm going to just put that on here. G is for giga, so that means billion. And that is the length of Earth history, the amount of time that Earth has existed. The rocks that we see along our coastline are mostly from the Mesozoic. and the early part of the Cenozoic. So they have formed over the course of mostly the last about 250 million years through a variety of processes. So when I talk about the geologic time scale, I will try to put it both in numerical time because that's easier for those of you who don't know the geologic time scale to interpret. But in the same way that you and I can say, we are meeting on February 19th, and you and I agree what February 19th is on the Gregorian calendar, geologists can talk in terms of late Cretaceous rocks and understand where we are in time. Because part of what we're trying to do is understand the order of operations. Like, when did certain events occur to create California and our coastline to eventually create the coastline we see today? So we have three different rock types that make up planet Earth. Igneous comes from ignite, like fire. So igneous is volcanic. And we have quite a few igneous rocks in our region. What we see in this kind of pinkish salmon color, that's all granitic rock. You can see it says mostly Mesozoic. And granitic rock is essentially the magma chambers that fueled volcanoes during the time of the dinosaurs. So the Mesozoic is the time of the dinosaurs. And at that point in time, there was essentially a series of volcanoes along almost the entirety of the coastline. And the magma chambers from those old volcanoes still exist and are now, some of them, at the surface of the earth, and we can walk upon them. So that has to be part of the story. We also need to consider the sedimentary rocks. And you can see here that in the coast ranges, there's quite a bit of this sedimentary rock in this super bright green color. It's also Mesozoic. So this Mesozoic sedimentary rock formed on the bottom of the ocean during the time of the dinosaurs. In fact, basically everything from the line that I'm drawing here over to the west, all of it was beneath the waves during the time of the dinosaurs. The coastline was significantly further east from where it is today. These sedimentary rocks, are made out of sediments. They're made out of broken pieces of rock. So that might be mud or sand or cobbles. And the rocks we're most interested in for our coastline mostly formed on the ocean floor. Most importantly, sedimentary rocks only form on the surface of the earth. So when we're looking at our sedimentary rocks, we're looking at either rocks that formed on the surface of the continent or the ocean floor, but never at great depths. And our third rock type is metamorphic, and metamorphic rocks form at great depth. And we definitely have some metamorphics in this kind of purpley color through here, that kind of dark purpley color. And it's not, doesn't show up very well, but we definitely have some metamorphics in our region along our coast as well. There's just not quite as many of them. And they are actually more from the Paleozoic. So they are the oldest rocks that we'll take a look at today. When geologists talk about rocks, we really are talking about the record of Earth history. And Marcia Bignard, who is a geologist and an author, said that rocks are not nouns, they are verbs. They record history, they tell us the stories of how Earth formed. So we learn about Earth history by interpreting the rock record to better understand how the rocks formed. But the processes that allow our rocks to form are really strongly tied to tectonic evolution. So the next thing that I'm going to maybe introduce you to, is plate tectonics, which is really the processes that allow the surface of the earth to move and lead to the formation of most of the volcanoes that we know of, and actually very much control the shape of the ocean floor. But these rocks also record landscape formation, including the formation of coastlines. Understanding how coastlines shift. If the coastline used to be back here at this line that I'm highlighting, I'll just zigzag it to make it clear. If the coastline used to be that far east and it is where it is now, that means our coastlines, that landscape is going to change over the course of time, and rocks will record those shifts in our landscapes. But we are focusing on the California coast. So we're going to be focusing on marine sediments. all the green stuff you see here, that's all marine sediments that all formed on the ocean floor. Within those marine sediments, we see chunks of oceanic plate, pieces of ocean plate, those fragments that actually ended up on the continent and can give us a history of the ocean. And we're also going to have to go further back in time to understand the magma chambers that formed in the Sierras, because we find chunks of those magma chambers at Point Reyes and Bodega Head, and even the Farallon Islands are pieces of those magma chambers. So they are important features along our coastline. But if we want to understand the development of a coastline and the formation of California, we really have to understand plate tectonics. So we have here on, I'm going to start in the bottom right, we have North American plate. And off of our coast to the north of us, so north of Point Arena and up through southern BC, Canada, there's a little teeny tiny fragment of a plate that we refer to as the Juan de Fuca plate. Then to the south, there's another relatively small fragment of plate that we call the Cocos plate. Both of those are going to come into the story, because both of those plates are actually converging with parts of North America, squeezing together, and that's causing those plates, both Juan de Fuca and Cocos plate, to dive underneath North America, and that leads to the formation of volcanoes. But here in between, this is the San Andreas Fault. Before the San Andreas Fault ever existed, it too was a subduction zone where the plate was diving underneath North America. That's what led to the formation of the volcanic magma chambers that we call the Sierra Nevadas today. So this map is really showing us 0 million years ago, as in today. But what if we went back to 190 million years ago? So this is like fairly early in the time of the dinosaurs. The very earliest dinosaurs show up 230 million years ago. So think of this as the time of like the big long neck Brachiosaurus. Over here we have North America, and this entire line that I'm going to trace, that whole thing is a subduction zone where you have one plate diving underneath another. The plate that is diving underneath North America is called the Farallon plate. Here, I have a video. There's no sound associated with it, so I'm just using it for the visual. But you can see heat from deep inside the earth is rising, and it forms convection currents. So it drags surface plates apart from each other. And where you have those plates pulling apart, we call that divergence. When you have plates coming together that are converging, one plate's going to go down. In this case, it's always ocean plate that goes down. So ocean crust forms at divergent boundaries, pulling apart, and ocean crust is recycled back into the mantle at convergent boundaries. But at these convergent boundaries, you have a plate going down, and it's getting hotter because it's getting closer to the core. It's getting closer to a heat source. And so the surface of that plate begins to melt. As a result, you end up with magma forming. That magma is relatively buoyant, and so it's able to rise, melt its way up through the crust, and erupt as volcanoes on the surface of the earth. So Indonesia, the Andes, the Cascades, the Aleutian Islands, all of those are subduction zones where one plate, always oceanic plate, is subducting underneath another plate. So if we go back in time, we know that the Farallon plate was subducting underneath North America. Another plate that's really important in the story is the Pacific plate. And you can see the Pacific plate is huge today. It makes up most of the Pacific Ocean. Both the Farallon and the Pacific plates are oceanic crust, so they formed at divergent boundaries and have been or are being subducted at convergent boundaries. So 190 million years ago, look at how cute little baby Pacific Ocean was. It was a Pacific plate was. It was so tiny, and it has become huge. But the Farallon plate, where did it go? There are still little pieces of the Farallon plate. It has not fully subducted. The Cocos Plate and the Juan de Fuca Plate are both the last remaining remnants of the Farallon Plate. And that transition from a big Farallon Plate subducting underneath California, Pacific Plate growing bigger behind it, and then following the Farallon towards the coastline is really the story of the development of our coastline. Because North America's continental crust, it's continental versus ocean, was formed by subduction zone volcanoes, uplifted accretionary wedge. I'll get to the accretionary wedge here shortly. And then the rocks that formed via subduction, both the volcanoes and the accretionary wedge, have since been smeared northwestward along the coastline. Because once the Pacific Plate met North America, rather than subducting, it formed the San Andreas Fault. And the meeting point of the Pacific Plate and the North American Plate, and therefore the San Andreas Fault, has literally smeared huge amounts of rocks to create the coastline we have today. We'll be looking at that in a number of different visuals. Okay. So really, when we're talking about the California coastline, we're talking about a tale of three tectonic plates. So here we have this Farallon Plate. I'm on the bottom left to start with. This is the Farallon Plate. Notice it's forming at a divergent boundary. Once that Farallon Plate meets North America, here's North America, it subducts beneath North America, and you have magma that forms and rises. And these subduction zone volcanoes, these are the Sierra Nevadas. This is what the coastline looked like during the time of the dinosaurs. Here you have the coast, and then this is the trench. And you've definitely heard of trenches, like Mariana's Trench. Trenches are the deepest parts of the ocean. On average, they're between 8 to 12 kilometers deep, whereas the vast majority of the ocean floor is closer to the average of 4 kilometers deep. And over here at our divergent boundary, which is a ridge or a higher point, is closer to 2 kilometers deep. But as that plate is sliding along, it ends up with huge amounts of sediment that falls to the bottom of the plate, mud, many little ocean creatures that when they die, they fall to the bottom and they form layers atop that Farallon Plate. And those layers are going to get scraped off at the trench. And that is best shown in the image on the right. Here you have the Farallon Plate in green. It's subducting. Here you have North America in brown. And in blue, we have that accretionary wedge. We call it a wedge because it's wedge shaped. And it's accretionary because the word accretion essentially says take many things and bring them together and make something bigger. So the analogy I use in the classroom is when you're taking the lint out of your dryer and you don't go to the lint tray and go lint 1, lint 2, lint 3. Instead, you kind of just accrete it into a ball and end up with a lint ball. Many small things come together to make something bigger. So the accretionary wedge is huge amounts of dead sea creatures, chunks of the ocean floor, mud, sand that flowed off of the coastline via rivers and made it to the ocean. Huge amounts of material just end up in these deep places on the ocean floor. And we call that an accretionary wedge. It has the sediments, broken pieces of rock, mud, and sand, pieces of the oceanic crust itself, and some of that plate is getting drugged fairly deep down into the earth, which causes metamorphic rock to form. So you get higher pressure and temperature. Therefore, it's a very complex mix of rocks, and we call our accretionary wedge the Franciscan complex. During the time of the dinosaurs, our Franciscan complex was underwater, so all below the waves. Right here, we have the Great Valley Group, so this would have been the relatively kind of calm waters off the coastline. And this accretionary wedge formed between approximately 140 to about 40 million years. So it had a very long time to accrete large amounts of material. So here we're looking in the upper left. This is a tectonic map of what Earth looked like 180 million years ago. Here's the Pacific plate here. So I'm going to draw a line. This is divergent. So you have Farallon plate moving away from Pacific plate. Number two, here's our Farallon plate here. So Farallon, Pacific is over here. And then our third plate is North America. And this darker line that I'm going to draw over, that's that trench. That's the subduction zone. The Farallon plate is going underneath North America, diving down, creating magma, and allowing those volcanoes to erupt. Those volcanoes, the Sierra Nevadas, the pieces of them that are along our coastline, we refer to as the Selenian block, just because it's essentially a section or a block of rocks that was first investigated in Salinas or Salinas area. That's where it got its name. These are literally chunks of cooled magma chambers that were forming as a result of this subduction between about 125 to 85 million years old. So that's the age of these volcanic rocks. Again, these volcanic rocks make up the Farallon Islands today, pieces of Point Reyes, and much of Bodega Head. So these Selenian block rocks start out here. I'm in the bottom left, forming those magma chambers. And this is what the Farallon block looks like, or the Selenian block looks like. Here we have chunks of very old rock. That's metamorphic. I'm going to come back to that. And all this salt and pepper stuff that you're looking at that's a little bit more white than it is black, that is the quote unquote granite. Now, we tend to simplify it and just call it granite because if you have ever seen a igneous, aka volcanic rock chart, the number of names on that chart would make most people cry. As a person who truly loves volcanoes, I love that chart, but I would not force people to look at that unless they're in a igneous and metamorphic petrology class. That's not this. So we're just going to simplify some of the names, or at least I'll help you understand what they mean. Granite is a simplified term for essentially the stickiest kind of magma. Diorite is also a fairly sticky magma, but it formed at a slightly higher temperature. And the only reason I point those two out is notice that our Selenian block, where those volcanic rocks are 125 to 85 million years old, meaning the magma cooled in that period of time, it's granodiorite. So we tend to hypersimplify and just say the Sierra Nevadas are made out of granite. And you can see this on the right side that they just call it granitic or granite. But technically, those rocks belong here on that rock chart, right in the middle on that transition zone between granite and granodiorite. So more properly, it's called granodiorite. I have no problem with you calling it granite, but some geologists might get a little angry. We know by looking at the minerals within those rocks that the magma chambers were between 25 to 40 kilometers deep when they were forming. So I want you to imagine that all of these volcanoes here in the Sierra Nevada would have had magma chambers beneath them. Now, those magma chambers are now the Sierra Nevadas, as in the magma chambers have lifted up to the surface. You and I walk on those magma chambers when we're in the Sierras. The chunk in here that I'm going to put an X on, notice it's darker. That is actually metamorphic rock. It's part of what we call the Sur series because it was studied in the Big Sur area. Those rocks are between 360 and 280 million years old. They're older, so those are actually from pre-dinosaur times. And those rocks are actually the remnants of marine sediments. So if we go back to 307 million years ago in this map in the center, this is what our coastline looked like. Whole bunch of islands, nice shallow seas. Essentially, we're looking at sediments that formed on the X that I just drew. And then much later in time, over 100 million years later, the remnants of those sediments end up being surrounded by magma and preserved in the deep places of the earth. So we now see them within that Selenian block. Now, the Selenian block itself, I'm in the right side now, is essentially the rocks that are to the west of the San Andreas. I should say specifically this part of the San Andreas that is north of the Garlock Fault, aka the Transverse Range, aka the Grapevine. Most people refer to it as the Grapevine when you're taking the I-5 up and over and down into LA. So we see this as this kind of green color. And all of the red that you're seeing in that, those are all the granitic rocks. That's all of the magma chamber rocks. But they originated from here. I'm putting an X with a circle around it. This is where they started. They started first at great depth. Then they got lifted up to the surface to where that X with the circle is. And the San Andreas has since moved those rocks northwestward to where they have landed today. So this is how our coastline has evolved. We're going back to first 60 million years ago. The star basically shows us more or less where the San Francisco Bay is. So here we have a subduction zone. Volcanoes would have been erupting. By 10 million years later, we're just zooming in a little bit. You can see that subduction zone a little bit more. The darker line I'm tracing is the trench. So these would have been the volcanoes erupting. You see a bunch of islands off the coast. 30 million years ago, we still have subduction happening on this north part. But what's happening off the coast of modern day LA is the beginning of the San Andreas. So there's still volcanoes associated with this point in history parallel to our coastline. Going down to 20 million years ago, here's the trench. There's going to be volcanoes to the east of that. But this place where you don't see that dark line anymore, I'm going to zigzag it. That is the beginning of the San Andreas fault forming. So when subduction ended, the San Andreas fault began to form, which will make so much more sense on the next image. Going to first 15 million years ago, the San Andreas fault literally grows northwestward. It starts in the south and grows longer to the northwest. And by 10 million years ago, the San Andreas fault had reached essentially the San Francisco Bay Area. Today, we still have subduction from Point Arena northward. So if you look for Lassen Volcanic National Park on a map, head straight over to the west, you're at Point Arena. From that point north, we still have subduction taking place. But everything to the south of that, down until you get to Baja, all of that is now San Andreas. So I come to the left side. In this buff color, we have North America. In the green color, we have the remnants of the Farallon plate, both to the north and to the south. And this pink color, this is pieces of North America that have essentially been captured by the Pacific plate. The Pacific plate is out here and are essentially getting smeared along the coastline, heading to the northwest, creating the coastal range. But what is the coastal range actually made out of? The coastal ranges are those Mesozoic accretionary wedge sediments, literally the sediments that formed in the deep trench when the dinosaurs were walking around and volcanoes were erupting. Those deep trench sediments have now been lifted up and are now the land we get to walk on, and it makes the coastline as we see it today. And all of this material is literally being dragged northwestward. And that motion of the plates sliding past each other is smearing the rocks against each other. So I want you to imagine the pink is smearing to the northwest, dragging those rocks northwestward. But you don't have to imagine it when you have a video, which honestly, so much easier than imagining. This is one of those videos you want to watch like 1,000 times until it starts to make sense. You have the Farallon plate subducting underneath North America. Think of the little triangles as pointing to volcanoes. Here we have the Pacific plate on the west. And you can see that piece of North America gets captured. It includes Baja, and it's being dragged northwestward. I'm going to push play again. Farallon plate, when it gets completely subducted, when divergent boundary meets convergent boundary, San Andreas is born. Now, San Andreas is neither divergent nor convergent, is a transform boundary. And as that transform boundary, San Andreas, forms, it literally smears the coastline northwestward. We can see that here in this kind of snapshots 30 million years ago. In blue, you have the Farallon plate. In yellow, you have the Pacific plate, and you can see they're being pulled apart from each other, while the Farallon plate and the North American plate are pushing towards each other, convergent. So pay attention to this arrow and this arrow, because they're both pointing in the same direction. So when Pacific plate meets North America plate, they're actually both moving in the same direction, but at different speeds. That's why the Pacific plate cannot subduct, it cannot follow Farallon down into the mantle. So you end up with the San Andreas forming. And as more and more of that Farallon plate completely subducts, the San Andreas gets longer and longer, but we see the remnants of the Farallon both to our north and to our south. I'm going to come back up here to the video. So we're looking at a tectonic transition from convergence, subduction zone, Farallon plate subducting. So think of volcanoes where those arrows are pointing to. And now it's going to transition to a transform boundary. We're just going to call it San Andreas. And everywhere you see in orange is essentially the rocks that are getting moved by the San Andreas, forming faults and valleys and mountains and volcanoes. It is dragging those selenium block northwestward and lifting it up out of the ocean as it goes, forming a series of faults that we call the San Andreas. So for 30 million years, the Coast Range has been uplifted and smeared, but it was once part of the ocean. It was all those rocks formed within the ocean. Okay, oops. So first we have to consider this tectonic development of our coastline, because that's such an important part of understanding why the coast looks like it does. So I'm going to come up here to 5 million years ago. We are here, so think of this as the future San Francisco Bay Area. There's subduction to the north of us, so the volcanoes are forming. And here we're looking at that captured piece of North America, captured by the Pacific plate, being dragged northwestward. Now, North America is going the same direction. It's just not going as fast. So if you look at my hands, essentially they're both moving in the same direction, but one is pulling forward. So you get a smearing action taking place. For 30 million years, that process of smearing has been taking place. It has created our coastline. But that has been leading to uplift, lifting those rocks out of the ocean. So most of that 30 million years of time, the erosion or the loss of the accretionary wedge shape has been happening underneath the ocean, as in ocean currents have been washing that away out to the deep ocean. It's only within the last 5 to 7 million years that those rocks have actually been lifted out of the ocean to end up being eroded subaerially, which is to me one of the worst vocabulary words there is, because it's not logic. I would like to replace that word with aerial erosion, because it's in contact with the air, and therefore weather and rain and rivers. Basically, it's above sea level. And so now we start seeing, for the last 6 million years, evidence of Northern California having rivers. And those rivers are reshaping those rocks that formed at great depth beneath the waves, that formed in the ocean, but are now part of North America. They're part of the continent. The next step in that story is looking at the most recent 2.58 million years. That goes all the way to today, because we are still in an ice age. The whole concept of the last ice age is actually one of my pet peeves, because when people refer to the last ice age, They're talking about the last time when the glaciers were bigger than they are today. But we still have ice sheets today. There's still Antarctica, there's still Greenland. So we still are in the ice age. We're just in a warmer time of the ice age. And the ice age has gone through these fluctuations between lots of ice and less ice and lots of ice and less ice. And when there's lots of ice, sea levels are lower. And when there's less ice, that melted ice flows into the ocean and the sea level goes up. So we've had more than 2.5 million years of sea level fluctuating because of the amount of ice on Earth is fluctuating. So when we consider how that's affected our coastline, I'm going to start here on the bottom right. This line is showing where the coastline was 18,000 years ago. That's when there was a lot more ice on Earth. It was one of the colder times, so sea level was lower. Notice the Farallon Islands would not have been islands. They just would have been high peaks, as in mountains that are part of the coastline. Here in the image that's bottom center, you can see this is essentially what it's depicting. This is between 17 to 20,000 years ago. Sea level was 120 meters lower than it is today, so about 360 feet lower. Here's the Farallon Islands. They're not islands yet, they're just part of the coastline. And everything that we think of as the bay, it's not a bay yet. It's just part of the land, it's just a valley. And we can see that over the course of time, 14,000 years ago, 11,500 years ago, that sea level has been rising this entire time. It doesn't always rise at the same rate, it can rise faster or slower. But as a result, our coastline, our entire region has shifted from essentially a river network to a flooded coast that has bays and has much steeper cliffs. So sea level has been shifting, but we still have that whole time tectonic uplift. Now, tectonic uplift causes emergence. Emergence really is just what happens when the land rises or sea level drops because both have the same effect. So my hands are here. Wiggly hand equals the water. If the water stays where it is, but the land rises, then you still end up with land higher than sea level. And so erosion is going to take place. Water will wash those cliffs out towards the ocean. Or I can keep the land at the same level and drop the sea. It doesn't actually matter in the end. The land ends up higher than the sea. And once you have land higher than a sea, then it's going to have more erosion associated with it. So we have all these marine terraces along our coastline, and those marine terraces and those cliffs are really the result of both the land tectonically uplifting at the same time that we have sea level moving up and down. And whenever I see a terrace, I know that at some point in the past, that terrace was at sea level, either because sea level was higher or because the land has uplifted, or both. And as a result, we have between our terraces our cliffs. So for the last 2.58 million years in our Quaternary ice age, Quaternary is really just a geologic time word. We have glacial and interglacial stages. Glacial is when it's cold, so I'm in the bottom right, lower temperature and lower sea level. So this has happened many times. Over 20 times we've had these glacial cycles. The last one was coldest at 22,000 years ago. And right around that time, we have our last glacial maximum, our last lowest sea level. So for about the last 22,000 years, our sea level has been rising because we've gone into an interglacial and in between the glacial stages. As a result of the rising sea level, headlands and islands are eroding. And we end up with what was once part of our coastline, as in part of North America proper, is now islands like the Farallon. And as currents flow by, it shapes those islands just as those same currents are shaping our coastline and changing where our bays versus our beaches are. When we look at our bays and our beaches and our headlands, they really are all forming as a result of the way that water's flowing along our coastline. But we can see that for the last 2.58, right through here, from this point forward, we have been in an ice age the whole time. And you can see sea level has fluctuated. The same time, the land has been uplifting. So we have two processes occurring simultaneously. And during the Pleistocene, there were the coolest ecosystems. So when we look at the Quaternary, which is a period of time that's 2.58 million years long so far, we break it up into two pieces. The first piece we call the Pleistocene epoch, and we associate that with like mammoths and saber-toothed tigers. And the last 11,700 years we call the Holocene, which is the time we still live in. So when you think of Pleistocene, that's when most all of the glacial stages, the colder times took place, but there were plenty of warmer times too. And when the sea levels were low, as is shown in this image we've seen, the places that we think of bays were all coastal plains. There were grassy valleys and freshwater marshes. The coastline was like 30 miles further to the west than it is today. And the creatures that would have been walking around at that point in time included California lions and dire wolves and saber-toothed tigers and scimitar cats with huge canines, short-faced bears and jaguars and mammoths and mastodons and horses and camels and bison and llamas and tapirs and moose. But the reason we don't see them today is that we do see a mass extinction at the end of the Pleistocene epoch. So the ecosystem shifts both due to climate reasons as well as due to the way that humans interact with the ecosystem. But the overall ecosystem was so different in the past. Therefore, when we really consider the development of our coast, we're looking at this change in tectonics, but we also need to consider that climate and changing sea level have played a really big role in creating the space we see today. So in the upper right, 22,000 years ago, I just circled, sea level was about 120 meters or 360 feet lower than it is today. And notice that sea level has kind of gone up in fits and starts, and that we've been at pretty steady sea level for the last 8,000 years. But if there's anything that we can learn from a graph like this, it's that sea level does not have to stay steady. In fact, it can rise relatively quickly. During the Holocene epoch, which goes from approximately, I'm drawing a second line on here, from here all the way over to today, that last 11,700 years before present, YBP is years before present. Temperatures have been rising in that entire time, slow and steady temperature rise until recently. And as a result of that natural aspect of that climate change, due to an interglacial cycle, the climate has gone from being really wet to relatively dry. So if we went back to the last glacial time, the bottom right gives us a map. Here's where our bay would be. But notice that this is the central California, and the whole coast range looks significantly wider than it is today. That's because it would be. But there's lakes all over Nevada and Utah. And what this map doesn't show is that there should be lakes pockmarking the entire coast ranges too. There would be a lot more rain, a lot more lakes. The climate was just colder and wetter. But that natural process of going from a glacial stage to an interglacial stage not only causes sea level to rise and therefore the coastline to move inland, but it also leads to natural climatic drying. And of course, to the formation of islands. So today, our Farallon Islands are islands, but they weren't in the past. And we can see this series of maps in the bottom left that as time has gone by, 13,000 years ago, 12,000 years ago, 10,000 years ago, that the coastline slowly shifted so that was what was once part of land now becomes part of the ocean. But we also need to consider our surface currents. I know that I'm running out of time, so I'm going to go through these last bits because I know that people who love the ocean tend to know more about the ocean currents. It's really important to recognize that California current moves from essentially north to south, more or less. And we can see that on the right side as well. And it's blue because it's cold. And that means our water is being sourced more from the polar areas. And the California current is one of our surface ocean currents. The surface ocean currents are defined as being about the upper 100 meters of the ocean, below which deep ocean currents do other forms of circulation. And these surface ocean currents are dragging alongside the land. And as they drag alongside the land, then they're going to create the shapes of not only the islands, but our coastal features. So, what actually causes the ocean currents to exist? It's really the wind pushing on the ocean, that frictional drag of wind pushing on the ocean. And notice here, this is a wind map. You can see that very loose flow of wind that matches up with this flow of water in our ocean current map. So as the wind pushes on the water, it creates ocean currents. But this beautiful circular motion that we see, those are called gyres, is the effect of both the wind and the Coriolis effect, the result of the earth spinning and how that causes the water to move in a circular shape. But that water is also having to drag along the edge of the continents, and that will lead to the overall ocean current patterns that we see in this map that I'm putting a star on. The gyres are just that circular flow that occurs because the earth is spinning, and we call that the Coriolis effect. But importantly for California, being on the eastern part of the Pacific, the eastern basin, we have that cooler water that comes from the north, and therefore our air is a little bit drier. If we had warmer water, then we would have more East Coast kind of summers. We would have much more humidity in the air, but we tend to have our slightly drier air just because we have colder water off our coast. That also brings us our very beloved fog. The fog is really the result of us having the colder waters. I'm going to pass over this because I know I'm running out of time here. So, if we want to think of our overall development of our coastline. I don't know why this red line is here and it won't go away. It's there. I'm going to show this video that looks at the development of the West Coast. So the arrow is pointing to where we are. And in the bottom left, you can see time. So 500 million years ago, 380 million years ago, this is when that Sur series, the old metamorphic rocks were forming. 340, 300 million years ago. Look at the dark line on the left side. That's the subduction zone. 280 million years ago, 245 million years ago. And we're starting to see some of those first volcanoes developing along what will become the coast of California. So I'm going to draw a line on here so you can see where the eastern edge of California is. It's hard to see it as we go deeper into this. Now the Farallon Plate is properly subducting beneath North America. So that line is showing us where volcanoes are developing 50 million years ago. You can see that darker line, that's subduction. 35, here comes the San Andreas. We'll see that coming from the south. Notice no dark line. 20 million years ago, here's the San Andreas through here. 15 million years ago, 10 million years ago, and 5 million years ago, and today. Tectonically, you have these shifts taking place. And if we were to project this into the future, how will these tectonic processes change the coastline in our future? Well, we don't know because the future is mysterious. But the possibilities, just based on the current plate motion, includes if San Andreas dominates, if San Andreas wins the plate tectonic game, then much of California, really the entire Selenian block, will become an island off the coast of California. Scenario two says actually most of that motion occurs on the east side of the Sierras. And so you can see that you end up with this big sea, the Gulf of California becomes larger. Or possibly scenario three, we end up with more of the pulling apart occurring further to the east, which would split North America in half entirely. We don't know, but the tectonics will continue to change into the future, just as we will see more change in sea level in the future. The potential sea level rise, if all of the ice on Earth melted, sea level could go up another 230 feet. If we compare that to Bodega Head, that would leave only the peak of Bodega Head as an island. The rest of what we call Bodega area would be all underwater. And we can see here in the bottom right, coastal flooding at the year 2100 in our future in two different scenarios, but essentially everything in blue would be now part of the ocean due to increasing sea level. That is a potential for the future just based on changing climates, but we also know that the much further future that our coastline will change as a result of tectonics. And then once you add coastal erosion and coastal currents in, there's that much more chaos in terms of our interpretation of possible futures. So I am quite sure that you have plenty of questions now. So before I start taking those questions, if you are interested in being aware of when I do more talks or walks in the future, please do feel free to sign up for my Appreciating Earth newsletter. I promise I do not send out a bunch of newsletters all the time. It's usually only like somewhere between 4 and 6 a year. You can sign up at my website, appreciatingearth.com, where I advertise all of the goings ons and also do a blog. So I'm going to check out the chat. Okay. So Doug asks, do you know how the Monterey Canyon was created? So when we look at both the sub-sea level, below sea level water flow of the San Francisco Bay, and we look at Monterey, both of those canyons would have started forming when sea level was lower. And so that would have allowed rivers to start creating a canyon shape. But a bigger piece of the reason the Monterey Canyon is so incredibly deep is because the Central Valley, what we call a valley, has not been a valley for very long in terms of geology. The entire Central Valley was an inland sea when sea levels were higher and the land was lower. Because remember, land is both lifting up and sea level is changing. So when that Central Valley was a sea and that water was draining out of the Central Valley, one of its main drainage points was through Monterey Bay area. It was not quite a bay yet, but that carved the canyon. So that's what created the depth of that canyon, which is now underwater due to sea level rise. Sarah asks, what causes one plate to go under or over a border plate? Oh, that's a wonderful question. So you have two kinds of crust. You have continental. I'm going to have my hand that has my knuckles up are the mountains because that's continental. And my flat hand will be the ocean. So these two different kinds of crust are really based on two different kinds of rock. I'm hyper simplifying this for sure, but our ocean crust is made out of mostly basalt, which is the same kind of rock that erupts out of Hawaii. It's really dense compared to our continental rock, which is mostly made out of granite. But what's more important than their relative density is the density of ocean plate relative to continental plate, and both of them relative to the mantle below. So you have the plates on top, and the next layer down is the mantle. My analogy that I always do in classrooms is a swimming pool. So in my analogy, you have a swimming pool. The swimming pool is the mantle. Now, you, as a swimming person in this analogy, you are the oceanic plate, and you're swimming along on the top of the pool because the density of your human body relative to the density of the water of the pool allows you to both float, but you are also perfectly capable of diving to the bottom of that pool. That's just because of the density of your body relative to the water. You can float or you can sink. The oceanic plate, because it's relatively dense, it can float and it can subduct or sink down. But our continental plate, its analogy is it's going to be one of those floaty rafts. It's floats by definition. So its density is lower. It can float very nicely on the surface of the pool, but it's too low in density to dive to the bottom of the pool. It's just not capable of it. It can't go down. It's too low in density. It's too buoyant. So if you have ocean and continent meeting, it's always ocean that goes down. Only ocean could go down. If you have ocean ocean plate meeting, whatever one is denser at that moment goes down. But if you have continent continent meeting, neither can go down. They're just going to overlap and squish together, and then you get the Himalayas. So, really, the answer to the question is density. Rowena says, I mentioned Point Arena as the point on the coast where subduction of the Juan de Fuca Cascadia subduction zone begins. But I think you meant Cape Mendocino, where the Mendocino Triple Junction is. So when you actually look at the tectonic map, Point Arena really is the end of the northern part of the San Andreas Fault. And that's where that triple junction is. So right around Point Arena is where we see it happen, but it's off the coast a little bit. And to the north of that, we have the Juan de Fuca. A portion of that is the southern portion is called the Gorda Plate. I will get to Sonoma State geology in a moment, for sure. Okay. Okay, so I'm getting to Sonoma State geology. So, as noted, um, Sonoma State geology is not in a good place right now. I don't know if you've been following the news, but Sonoma State is, my words, imploding. Due to budget crises and incredibly poor administration and management for quite a long time, they have decided to close a number of departments, including geology. And as a result, this will be my last semester teaching at Sonoma State University. Really, I wish I had explanations, but the truth is, none of us understand what's going on. The decisions that are being made don't make sense to anyone with any logic skills. So, when it comes to geology departments, we have kind of one last attempt is on Friday. There's a meeting to attempt to reverse the decisions administration has made in terms of closing departments, including geology. But unfortunately, this very well may be my last semester teaching. So if you are interested, please do reach out. I can give you information about the meeting that's happening on Friday. And there are plenty of people who are also been writing letters to politicians and to the school and just trying to get people to realize that this course of decision making about the university not only doesn't make sense, it's there are other options. Does anyone have any other geology questions? Nothing?
Questions? This is
Yeah.
Karina here. Yeah, I am wondering. I've heard about the way Point Reyes is situated. That essentially, like you were talking about, and I love the metaphors here. You mentioned something about how the for millions of years California has been uplifted and smeared.
Do you
What a
like the smearing?
and that North America is going in the same direction, but not as fast as California. Appreciate that. So thinking about that and how the big one we think about these big earthquakes, how fast could it happen that there would be a big change to the landscape, something like a big tectonic event that would cause a place like Point Reyes to actually break off and move in terms of time? Is it all in a at a glacial pace?
Oh,
Or could it happen more quickly?
Oh, that's such a good question. So, when we think of tectonic motions, the earthquakes we experience are just the tectonic motions. So every earthquake is moving the plates. Really, what an earthquake is that the plates have been moving. So my elbows are going to be like the plates. And the plates are going to keep moving. But if the plate is locked, I'm going to try it this way. If the plate is locked and the rocks can't slide appropriately, eventually so much strain builds up that it breaks. And that's what you and I experience as an earthquake. So ideally, when the plates are moving, the rocks just let it move and we get no big earthquakes. It's just a gentle motion. It's really that if we get these locked zones, then it's going to unlock like that. And you and I experience that as an earthquake. So during a really big earthquake, we could get many feet of motion all at once, but it's going to take many, many, many millions and billions of earthquakes to create the tectonic motions we saw in those videos. Those are really the sum of many millions of years of many millions of earthquakes.
Fantastic. Okay, I have one more question.
Yeah, go for it.
So what do you think is some of the most interesting and important conversations happening in the field of geology today? Where are you most paying
Oh,
attention? What do we need to be knowing about?
oh, that's such a good question. I think some of the most interesting the things that are happening is really our increase in technology, like the way that science is advancing and our ability to look to greater depths within the earth. So, if you have any memories of like sonograms in the 1970s of like blob baby inside a belly, like all you could see was a blob and it was moving. That's what the sonograms could show us. And today we can literally get the face of a baby still within the womb. We can see amazing degrees of detail because our tools have just allowed us to see that detail. When I think of where we are with plate tectonics right now and our ability to use remote sensing to look deep, deep into the earth, then essentially um, we're kind of in the 1970s sonogram era, but in the last few years, we've progressed towards the 90s and we can see so much more detail at depth than I ever imagined would happen in my lifetime. So, for example, we now can see the remnants of subducted plates. They still look kind of blobby, but the remnants of subducted plates down at the bottom of the mantle, which means that in the next 20 years with more advancements in science that we will be able to better understand what the internal layers of the earth look like that much more, which means we'll understand how the plates move in more detail. And my hope is that that increase in technology might also eventually lead to better predictability of earthquakes, because at this point we have long-term predictions that say the plates are moving, earthquakes occur along faults, an earthquake will eventually happen statistically, this size earthquake in this period of time. But there is no technology at this point that says we should expect an earthquake today, tomorrow, next week. It just doesn't exist. But with increasing technology, maybe in my lifetime, maybe a couple more lifetimes, we can get there. But I also think that the way that geology can help us understand climate change, because literally the rocks are the record of the past climate. And so our understanding of climate change over the course of billions of years is geology. And to use that knowledge to help us understand how to solve some of our climate problems going forward, I think we're going to find that rocks not only give us the clues of how to do that, but they become also the tools that we can use to undo some of the damage that's being done.
Super cool. So, yeah, what I it was a real pleasure getting to go into a space of a time and a speed and a perspective that was this big. It was very, very helpful. I know for my nervous system, and I hope that other people got that experience as well. I love that people are asking where this will be recorded and shared. It's all available on our website, and we will, as Trey just mentioned, we will have it online in a few days. We're super grateful if you are able to help to donate to support Nicole's presentation and our ongoing science presentations. Nicole, it would be very fun to have you come in sometime and get to engage with you further in person. It was very cool that this community is keen to know more and more about geology, because geology dictates what life can happen here and how our ocean is formed, and what creatures live here and how, and who we are, and our even our culture and identity is dictated by geology and geography. So
So true.
really, really great that you were able to come, and we're super grateful for that. It looked like there was one more question that just flew
On
by. It looks like
Yeah.
a few people are asking last minute questions. Okay,
Yeah.
you would be
Yeah.
willing to be
So
generous.
there was a question about the periodicity of the Cascadian subduction zone. So essentially, how often do really big earthquakes occur on the Cascadian subduction zone? First, subduction zones always produce the big earthquakes. Like every 9.0 earthquake that's ever happens on a subduction zone. And when scientists talk about the big one, we're not talking about the San Andreas. That's not going to produce the big one. The Cascade subduction zone will. And the last time a very large earthquake occurred on that subduction zone was January 26th of the year 1700. And I think you should very much go, how could you know that? The earthquake was probably around a 9.0, but it was big enough that it did two important things. It dropped the coastline and drowned an entire forest. And that forest, the tree rings could be dated to the year 1700. But it also created a massive tsunami, which made it all the way to Japan, and Japan recorded it on January 26th. So between the tree rings, that's a paleo record, and the historical record from the Japanese tsunami records, we could figure out the exact date. And by looking at a longer term record, it's about every 300 to 400 years. So anytime now, this is why there's a concern about the big one. But keep in mind, you can't do anything about it. And that we have a warning system. We not only have an early earthquake warning system, we are the first generation in all of human time to ever have early earthquake warning. We also have a tsunami warning system, and we are of the first few generations to ever have that. So I know that the events that occurred in December turned people off from the whole tsunami earthquake warning system, but it worked. It's just still being developed. And I would much rather have a warning that is giving me a clue of a worst case scenario that didn't happen rather than no warning system at all. So if you haven't looked into My Shake, it's out of Berkeley Laboratory. My Shake is the app. That's how you would actually get the first line of like warning that an earthquake has started. The tsunami warning system is based on that. And I totally forgive them for giving us a slightly false warning about tsunamis happening in December. Because the truth is, it could have developed into a tsunami, but they didn't know. So they had to put a warning out. Because what if they didn't put a warning out and a tsunami did occur? Then we'd be blaming them on the other end. There was another question. Oh, do I have any recommended reading sources? So on my website, on appreciatingearth.com, I have a San Francisco geology webpage that has a whole bunch of geology sources on it. I also have another webpage that is like recommended documentaries and books and the things that I love that maybe you will too if you are the right kind of geeky. But my website has a lot of information. It's been called a rabbit hole. There's also an entire page just on like recycling and reusing. So I hope you find those resources helpful. And again, thank you so much for inviting me. It's always fun to share with an audience like this.
So again, everybody, thank you so much. Drop us a line if there's other areas you're all interested in learning about, and we'll see if we can find people to give you good talks like Nicole just did about geology. It was fun seeing so many familiar and new faces here tonight. So thanks for being a part of our community. And especially to you, Nicole, for being a part of our community and joining in and giving us a new perspective and time frame and speed to be looking at the Earth today. It was very, very helpful, and I learned a lot. I hope all of you did. And I'm going to go look up dire wolves, scimitar cats, and short-faced bears now, and so much more. So thank you again.
Thank you too. Have a wonderful night.